what's going on YouTube? What's up? My name is John. If it's your first time here, welcome to my practice stream. My thing is I love to do practice streams, so I'm just going to be practicing math live, and there's going to be all sorts of mistakes left and right in this, but hey, that proves that I'm a human. I'm not ChatGPT. I'm just a guy who likes to practice mathematics. So, welcome. Today is January 30th. It is Friday. It is very cold. And we are going to be starting Chapter 2 of Frale. This book is my favorite book so far on linear algebra. It's the book that I learned an introduction to linear algebra from in my undergraduate. And I'm just going to say, I like it better than string. Like, a year ago, I tried working through string. I like this one better. I think it's nicer. It's written more for, like, an undergraduate or, like, first or second year math student. And also for engineering students. But it has, like, a mathematician's kind of level of organization, clarity, structure. Yeah, I don't know. I think it's just a really nice book. So, let's get started. If it's your first time here, well, welcome, first off. The way I like to review and relearn these topics is by just going straight to the problems. So we're just going to be going straight to the problems, and I'm going to try to solve every problem in this book. So thank you for joining me for that. We are starting Chapter 2. We're getting closer and closer to vector spaces. In Chapter 2, we're going to start learning about linear transformations, which is pretty cool. First, we're going to start out defining dimension and rank. Yeah, dimension, rank, and linear transformations. So, I've already done Frale 1, or 2, 1, 1, so let's do Frale 2, 2, 2, 1, 2. That's what I meant to say. 2, 1, 2. Here we go. Argue geometrically that any set of three, what's it called? Distinct. Oh, I forgot to turn on the dual live today. Shoot. I don't think I should restart just for that. That is so annoying that I can't start it in the middle of the stream. That's so annoying. Oh well, whatever. Okay. That any set of three distinct vectors in R2 is dependent. Right? Ooh, geometrically, that any set of three distinct vectors in R2 is dependent. Like, for this to be the second problem in this chapter, that's nice. This is like a legit, like, mathy kind of problem. Okay, geometrically. Well, a vector in R2 is, let's see. The span of a vector, this would be better. The span of a vector in R2 is a line. Geometrically. I mean, it's really that, yeah, if they were independent, then I can do it algebraically pretty straightforward, or I could try to argue from the rank of the reduced matrix, but geometrically, any set of three distinct vectors in R2 is dependent. So if we have in R2, this is two-dimensional space. If I take one vector and I take another one that is not on that line, so the span of this vector is a line, in R2. And if I choose any other vector that's not on this line, choose another vector not on that line. I guess I should say the span of a non-zero vector. Because a zero vector is just the point at the origin, right? But yeah, the point at the origin is on the line for any other. Choose another vector not on that line. It creates another line. How can I argue geometrically? Let's see. Let's see. If it's the zero... Well, I have to say it's not on that line, so therefore it's not the zero vector, right? It spans another line in R2, right? So we have another line that, yo, good morning, Mateus. Mateus, how are you, man? Good to see you. Welcome back to my practice stream. Okay, so it spans another line in R2. And then I want to just say, like, choose another and it must be a combination of the first two, but that's circular. That's like just, I'm not proving, like, I'm missing the step that is, that says, geez, I don't know. Let's see. Argue geometrically. Can I just say that the span of V and W, maybe I name these V and W, has dimension 2, and R2 has dimension 2. Therefore, a third vector must be a linear combination of V and W. I.e., if we have another vector, TU, V, W, X, maybe U is in the span of V and W, right? I could rename all of them so that they're in order, U, V, W, but whatever. Something just still feels like a little circular about this argument, but good enough. Let's move on. I wonder, in the back of the book, is there a clear answer? Look at that. This book has a floppy disk in the back. Look at that. A floppy disk. Ha! I love it. How retro. Heck yeah. Mateus, I hope you're having a good day, dude. Let's see. It says answers to most odd-numbered exercises. So we didn't... This one does not. Let's see. How can I argue geometrically that a third line how can I argue geometrically that I can kind of like combine lines to generate any other line? Well, let's take a point. Right? I can certainly add some, let's say, okay, here we go. I think I'm getting to something. Okay. Any point on another line, let's say this point right here, can be, and I'm going to make this a little more clear even. So let's say that V is like this, right? We can scale V so that we get this point. Well, we've got this delta between this point and this point, right? So this didn't quite work exactly, but if what I'm trying to get at is that there's some scalar multiple of this one such that we get so much of this. Like we can create some sort of right triangle sort of thing, I think. Let's see. Maybe right here or something. So then, this is pretty sloppy. This is not, I'm getting somewhere with this. You want to create some kind of right triangle, I think. You want to do some kind of right triangle. That's not the right triangle exactly, but it's something along these lines, I think. Thinking about how you can take those two, choose any point on this new blue line, or choose, what I'm really doing is I'm choosing, excuse me, I'm choosing this new vector, and I want to see it as an addition of these two other vectors, of some multiplication of the other two. So we have this right triangle here, and let's see. I don't know how to get this geometrically. I think I'm doing this like a little more in a more complex way than what Frale may have wanted. Any set of three distinct vectors in R2 is dependent. It's like the kind of cheat code here that I might be using too much power on is that this is dimension 2, and a set of 3 in a 2-dimensional space must have dimension 2 as well. Like, yeah, I don't know. Let's move on. Let's just move on. I'm going to call that done. Good enough. Nobody's actually grading these homework sets. So, where's my pen? Where did my pen go? It's been a while since I last saw a floppy disk. I don't remember the last time I've seen one, man. That's so cool. That is so cool. I saw a floppy disk today. Frale. 2, 2, 2. Let's see. All right, so A is 5, -1, 0, 2, 1, 2, 1, 0. I have a question. Do you, Mateus, if you're still there, man, what do you think of the look and feel, visually? How do you like the way that the stream looks if you can see me talking, or would you prefer if I am off camera and you can still hear me, but you see me playing the guitar in the background? Let me know. What do you think? Does this create like a different vibe? Okay, so we got Frale 222. 5, -1, 0, 2, 1, 2, 1, 0. This can help me promote my guitar channel that I also run. 0, 4, -1, 2. 0, 4, -1, 2. Okay. And now he's asking us to find A, the rank of A, and then B, a basis for the column space of A. Yoink. And then C. Oh, wait, no. I got this wrong. Okay. This one is not the column space. He wants the row space first. Not that it matters. A basis for the column space. And then D, a basis for the null space. Okay. Guten Morgen. Hey, SB practices, what the hell? I really like to see you think. Okay, but yeah, it seems a really good try to reach a new public. Guten Morgen, SB practices. How do you, okay, yeah, you got a what the hell reaction to that, so, okay. I just don't know, like, do people want to see me just being, like, confused, like, looking and being like, I'm stuck? Like, do you like seeing me? If you all like seeing me think, then yeah, sure, okay. Oh, you're getting a lot of lag? I'm sorry to hear. I can't solve that. Let me know if I'm lagging for you as well, Mateus. Maybe it's on my end, but I don't know, I don't think so. Okay, so let's find the rank of A. So, we're going to do linear transformations until it is in, at least row echelon form. Yeah, it's all good for you? Okay, cool. I want to swap, I like working with 1s in the first row if I can, or in the pivot entries. So let's swap those 2 rows. I'm going to go ahead and subtract 3 times the first row from the third row. I mean, here it's 3 times this minus this. but then I swap them and then I do that operation. So 3 minus 3 is 0. 1 minus 6 is negative 5. Negative 2 minus 3 is negative 5. 4 minus 0 is 4. And then this last row, we still have 0, 4, negative 1, 2. Okay. 1, 2, 1, 0. Let's subtract 5 times the first row from the second. Maybe I'll write these operations. So this is R2 minus 5R1. Why am I being mean to you all? Let's see. Here I wrote that this is R3. Here, is that right? No, this was R2. So I transposed the second row. I replaced row 1 with row 2. And then I also did R3 minus 3 times R2. So the third row minus 2 times the second row of the previous matrix. I'm sorry, Sid. I'm sorry to hear, dude. I'm sorry. I don't know what to tell you. I don't know what to tell you. Okay, so what I'm noticing, I don't like... Can I move this thing around? No, I can't. I'm having ideas on how to make this visually cooler. Here, I break the illusion that this is just like a black whiteboard a little bit, but you can see like the scroll bar in the right. I'm getting distracted, I know. Let's yoink and get rid of that. Yeah, you can't see that scroll bar in the bottom right now. And now I'm trying to decide, do I want to cut out that thing in the top right? Like those buttons? I don't know if it's worth it. And then I can get a little bit bigger over here. I want to make sure that the iPad still always fully shows up, or like that the I don't know what I'm trying to say. Don't worry about it. All right. Yeah, that I'm not covering the iPad with the camera. All right. What are we doing again? We're doing replacing row 2 with row 2 minus 5 times row 1. So 5 minus 5 is 0. Negative 1 minus 10 is negative 11. 0 minus 5. And 2 minus 0. While we're at it, I think 0, 4, negative 2, negative 1, 2 is going to be easier to work with than 0, negative 5, negative 5, 4. I don't know if that's true or not. 1, 2, 1, 0. I don't know. I don't think we need to go all the way to the end, but maybe we do. Let's 0, 4, negative 1, 2, 0, 5, 5, negative 4. I prefer to work with positive numbers. So I replace the second row with the third row. And then I replace the third row with negative R4 here. And then I'm going to replace the last row. I'm swapping it with 0, 11, 5, negative 2. So this is negative R2. Yep. So I'm doing like a few operations all at once. rather than like always doing just one step at a time, which is incredibly tedious. 1, 2, 1, 0, 0, 4, negative 1, 2. And now we get to this nice moment when we're going to do 4 times row 3 minus 5 times row 2. Okay, so first entry is 0, and now we have 20 minus 20, 0. We're going to do 20 plus 5. 20 plus 5. And then we have negative 16 minus 10. Right? Negative 16 minus 10. And then we still have this one. We can frickin' let's go ahead and do it here as well. We've got 4 times row 4 minus 11 times row 2. So we have 44 minus 44 is 0. My goal is to try to get these entries to be 0 below. So in column 1, I have that pivot. Now I have this pivot. And then the goal is to get zeros below those pivot numbers. So we have 20 plus 20. I confused myself. 20 minus 55. 20 minus 55 is negative 35. Right? Yeah. Negative 35. If I did that right. And then negative 8. Negative 8 plus 44 is 36. Okay. Yeah, these problems are they're just not trivial. Like, we're getting some kind of meaty freaking numbers. At this point, I think we can clearly see that 25 negative 26 is not a scalar multiple of negative 35 36. Right? I think we could. I can see that. I hope you can see that. So therefore, I think that we're done. We don't need to get this to reduced row echelon form with ones in the along the diagonal. But if we want to find the basis for the null space, we want to ultimately. But at least at this point, we can answer some of these first questions. For 1, the rank of A is going to be 1. For 2, a basis for the row space, we can choose these rows. Yeah, we could choose those rows. Yeah. And then 1, 2, 1, 0. Zero, 4, negative 1, 0, 4, negative 1, 2. 0, 0, 25, negative 26. 0, 0, 25, negative 26. And 0, 0, negative 35, 36. 0, 0, negative 35, 36. maybe it's not the most elegant basis ever for the row space. Like these 25s, 26s, I don't love these numbers, but that's, you know what? Who cares? Who cares? We got better things to do. Basis for the column space is then going to be, let's use a different color. Each of these columns, we can either write them as columns or as rows. It doesn't matter. It's still an n-dimensional list of numbers, right? 1 0 0 0. These are still in R4. 2 4 0 0, which, let's get a little more elegant. This is the same as 1 2 0 0. If you take half of that second row, or the second column, 1 negative 1, 25 negative 35, 25 negative 35, and finally 0, let's divide that column by 2, 0 1 negative 13 and 18. Okay, so that's a basis for the column space. Now, basis for the null space is the trickiest one. Oh, well, no, if this matrix is freaking... If this matrix is a rank 4 matrix, am I crazy to think that it ultimately... Yeah, if it's a rank 4 matrix, if I can see right now that third and fourth rows are not linear combinations of each other, then we can do more row operations. And eventually we're going to get to 1 0 0 0 0 1 0 0. We're going to eventually row reduce this, and it's tedious to do it by hand, but we got to, like, this is the first time that I feel confident for sure that this matrix has rank 4. And if it has rank 4, then it's going to ultimately reduce down to the identity matrix. So yeah, we could have much nicer bases for all of these things. So scratch that. Much nicer one is going to be 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1, right? Pretty sure. Binary solo 0 0 0 0 0 1. Yeah, dude, if you want to talk about binary solo, we were literally doing binary codes yesterday, right here, like 001, 001, 001, 011, 010, 101, 011, 110. I kept, like, saying all of that again and again yesterday. It was a little crazy. What's up, Leroy? Good to see you, man. Yeah, we were doing, like, some wild, true, like, binary number stuff with these Hamming codes for the last couple of days. There's one spot where there was just an insane, super tedious amount of this. I was writing down all of these, and I was just saying it, and I was hungry. I was late to eat lunch, and I was just like, I was just like, kill me now. Like, I am so sick of saying ones and zeros as I was writing all of that. But hey, we got through it, and now I'm better for it. And it's permanently recorded on the internet. Okay, so basis for the null space. The only zero vector is just 0, 0, 0, 0, I think. Is that how these things work? Is that how this works? I think so. Yeah. Basis for the column space is again going to be the same thing. Let's see, where are we? I don't know, another color. We're running out of colors. A basis for the column space. Oh, here we go. Basis for the column space, forget about that one. That one sucks. This one. Use this really nice clean one. Alright, I'm gonna go ahead and call this done. Done. Boom. Now, 2.3. Frale 2.3. I still don't feel like I've gotten stuck yet. Leroy, it's good to see you, dude. Good to see you. We got Frale 2.3.2. I think I did 231 before. Yes, I did do 231. So this time we're going to do 232. Hell yeah. Hell yeah. I just didn't cross it out in my book. Okay. 232 asks, is T a transformation of x1, x2, x3? So this is like a constant function, like doesn't matter what, for this machine T, you know, you give it a nice, beautiful vector and it always gives you back 0. It just always returns 0, 0, 0, 0. And this is asking, is this a linear transformation? Yes. Why or why not? Let's make that mathematical argument here. How do we know that something is a linear transformation? It needs to satisfy two properties. One is that T of U plus V. What the hell? Wait a minute. Oh, yeah. I'm a dummy. Okay, here we go. T of U plus V is the same as T of U plus T of V. And then secondly, T of KV is equal to K times T of V. So it needs to preserve, in other words, preserve addition, and it needs to like preserve scalar multiplication. So yeah, you can add on the inside or do two different transformations and add them. Well, I think that this is pretty clear to see. For any two vectors u and v, this is 0, and t of u plus t of v is 0 plus 0, and that is also 0, right? I'm being sort of lazy in a sense. I'm writing 0 instead of 0, 0, 0, 0, 0, but really this is 0 in R4. Like, we want all these properties of 0 to be true. We want always 0 plus x equals x in any number system, in any kind of like math setting. That's an important thing for 0, I believe. Okay, so then A is true. And now B, if I multiply a vector, well, okay, I mean, T doesn't care. T does not care about your scalar multiplications. And it returns 0. T always returns 0. It doesn't care what you give it. This is k times 0, and then that is still 0. So, voila, we're done in both A and B. Frale 232 is done. Done, dude. Permanently written in my book. Look, hey, Leroy, check this out. First off, everybody, Leroy knows this. I'm writing directly in my book. Isn't that insane? Aren't I like a madman writing directly on my paper book in pen? But then the thing I really wanted to show you, I found this today. This book has a floppy disk in the back, dude. This book has a floppy disk. That's so cool. I haven't seen a floppy disk in a long time, man. It's not just a CD, which also feels incredibly retro. It's a fucking floppy disk, dude. That's awesome. All right, so I'm not reading any of these sections. This is going to be the first time that I'm trying Frale 2.4.1. Boom. These were problem 2, but I got stuck last time. I forgot what a linear transformation was, which is embarrassing, sort of, but why not? I'm an adult. We're allowed to forget math. And now I'm reminding myself about math. 2.4.1. Explain why the linear transformation TA, which maps from R2 into R2, where A equals 1, -3, 2, -6, has the line y equals 2x as a range, but is not the projection What the? I don't know what the... What? Okay, explain why the linear transformation this, where A is this, has... So I think it... I think I can see that fairly clearly. So if we have AX, if we take a vector and multiply it by this matrix, 2, -6, I'm going to name the vector xy, like that. Then this is going to return a two-dimensional column vector, x minus 3y and 2x minus 6y. Here, wait. What am I doing? Okay. I think what I'm supposed to do on this is see what happens. What does A send the two different basis vectors to? So when x is 1 and y is 0, we have 1 and we have 2. Right? When y is 1 and x is 0, the first entry is -3 and the second entry is -6. Right? So then the point 1, 0 right here gets mapped to 1, 2. Right? And then the point 0, 1 gets mapped to 1, 2, 3, 1, 2, 3, 4, 5, 6. And then any, hey, good morning, Leo. What's up, Leo? Dude, I am struggling over here, bro. Okay, so explain why the linear transformation, this equals this, where, okay, these are a scalar multiplication of each other, right? This one is equal to -3 times 1, 2, right? So, I can kind of geometrically see that they're on a line. Like, yeah, if this is a vector, the first one, I can wonder, like, okay, is the other one on the line that goes across 0? And it is. So this is the line y equals 2x. And that's where we got here. Y equals 2x as a range. But this part is what's confusing me. But is not the projection of R2 onto that line. What does that mean? Dude, like, Leo can probably explain this to me. Because, like, it seems to me like this is freaking projecting R2 onto that line, right? Like, any vector that like, here we chose the two basis vectors to be simple, but like, if I choose any other freaking vector or any other point, isn't that going to map somewhere on the line? Like here, why don't we just see this example? I just did a wild guess of that. I don't think that's true, but 1, 2, 3, 4, 5, 6. Let's call that 6. Let's see what this maps to, just out of curiosity. -1, 2, 3, 4, 5, 6. Yeah, this is roughly -6, 6. Why not? What would a times -6, comma 6 equal? Well, I could see that it's going to be 6 times, -6 times this one, if I'm fancy, plus 6 times this other one. But let's not be fancy. Let's just do it straightforwardly. 1, -3, 2, -6. This matrix multiplied by -6, comma 6. Let's do it the straightforward way. We got -6 plus -18, which is -24. And then we have -12 minus 36. What the heck just happened? Oh, low battery. Okay. -12 minus 36, right? Which is -48. Well, it's going to be hard to see that that's on the line, sort of, but not really, because it is true that this is y equals 2x. -48 is 2 times -24. Oh! Okay, wait. Why isn't it a... Okay. I think that it transforms R2 onto that line. It does transform R2 onto that line. I'm just like looking for the definitions here. A projection of R2, this was like the very first thought I had, honestly. A projection of R2 onto that line would mean, like, am I crazy to think that that would mean the X and Y component? I mean, the first projection, the projection of the first... I'm confusing myself right now. I'm getting a little dummy. The projection would match each point to the point on the line it is closest to. Yes. Okay. That's what I'm getting at. I was like, oh wait, I mean, like, we're like projecting either in these directions or maybe projecting in like the closest direction. But no matter what, yeah, okay, so it would be the... I was thinking it's like either projecting to the point on the line with the same first or second component, or it's using the minimal distance like this. Yeah, but none of these three possibilities, which would make sense as projections onto the line, none of those are the one true mapped point, which is all the way over here. I think that's good enough for me right now. I think I understand that. Yeah, the projection would map each point to the point on the line it is closest to. So 1, 0 would map to the point on the line in which that line segment between 1, 0 and the point is mapped to is orthogonal to the line. Yeah, exactly. So, right, if it were projected onto that line, it would be orthogonal to the line. Like a nice little right angle right there. But in truth, this point actually maps to this other point. What was like sort of tripping me up was that in this case, the x component is preserved. Like 1, 0, like the projection, it was a projection onto that line, coincidentally projecting like the first component, but not the second. So like, yeah. Oh yeah, possibly it could project via different angles. Yeah, I mean, I'm just like trying to imagine what would be in this book at this point. Like, would Frale try to define projection as like minimizing, you know, the distance to another line, like in this section? Linear transformations of the plane optional. Okay, there we go. There's the freaking word that I'm looking for. There we go. This is an optional section. So, there we go. It would make sense for him to define projection onto a line as like the minimal orthogonal point. But that's not always taught in like a standard like introduction to linear algebra. Yeah, okay, here we go. It's because this is an optional section. He must have. I'm not reading the sections. That's my handicap that I'm giving myself here. All right. Collapsible, non-invertible, projection on the x-axis, projection on the y-axis, collapse. Neat. Okay. Yeah. Okay, so we're getting to what I was imagining is in the book. He doesn't use the symbols pi 1 and pi 2, but he does call this projection onto the x-axis 1, 0, 0, 1, projection onto the second, onto the y-axis 0, 0, 0, 1, right? Collapse. He also gives this example, collapse onto y equals negative x, negative 1, 0, 1, 0. And he gives this other example, collapse. I haven't heard that term. Collapse onto y equals 2x is 1, negative 3, hello Luna, 2, negative 6. So this is collapsing onto y equals 2x. This is the same matrix, right? 1, negative 3, 2, negative 6. Neat. It's not a projection onto y equals 2x. It's something called a collapse. Yeah, exactly. Hell yeah. I was about to look at the section, but here we go. He defines projection of the plane on the line L through the origin maps each vector v onto a vector p represented geometrically by the arrow here's the keywords that we're getting, that we're looking for, that you were absolutely right on. Thank you, dude. By the arrow starting at the origin and having its tip at the point that is closest to the tip of V. And then he has this nice little parenthetical that's like phrased entirely in terms that's closer to what you said, in terms of vectors. The vector v minus p must be orthogonal to p. Hell yeah. Okay. So we've got, he defines projection matrices, and then does he have a definition of collapse, or is it just like a transformation onto that line? I guess that makes sense. Like collapse, like all of R2, all of the points in R2. I mean, this -6, 6 went somewhere super far this direction. Oh wait, it would have been -2, -24. It went way out somewhere this direction, and in truth, not over here. But yeah, every point in R2 maps somewhere. Freaking maps somewhere on this line. But yeah, not necessarily in a direct line, in a direct orthogonal direction to the line. Okay. Let's see. Projection. Oh yeah, possibly project via different angles. In that case, you need to show that the angles between A to AA and B to AB are different. The projection. Although the space of all projections onto a line wherein you project via some angle would be a one-dimensional space, but the space of all linear maps onto the line is two-dimensional. And you gotta go to work. Dude, thank you for stopping by. Have fun. You have fun at work. I should probably get to work myself, because this is just free content for the internet. But if you join me on my guitar stream, you can tip me. I have memberships, and I would be happy to write your name on my guitar if anybody wants to drop a little donation. Thanks for watching, everybody. My name is John. It's a pleasure to be hanging out and practicing mathematics with you all. I had fun. I would say we got stuck on this problem. Even though we kind of got through it, I needed a hint from Leo and from the book. But I was basically there. I was basically there thinking like, hey, this does not look like a projection from that point to that point. And then there's like a very good counter example. So, heck yeah. All right. Thanks for watching. I gotta go. Bye.